Alright, so in this video, we'll be looking at section 7.2, which is volume either by the disk or washer method. So in the previous section, we looked at applications of the integral that involve finding the area. Now we're going to look at applications of the integral that involve finding the volume of a solid of revolution. So the first section we'll look at here is the disk method. So let's go ahead and get started. When any region in the plane is revolved about a line, the resulting solid is called a solid of revolution, and the line is called an axis of revolution. The simplest such solid is called a disk, which is formed on revolving a rectangle about an axis adjacent to one side of the rectangle. In other words, the axis touches the rectangle. So say I have some line here, we'll call this the axis of revolution. And I am going to draw a rectangle here. And I'm going to go ahead and color it in as well. So this rectangle here, the idea is that we're going to revolve it around the axis of symmetry, or axis of revolution, and it will create a disk, right? You can imagine taking that rectangle, wrapping it outside of the paper and back into the paper, and creating a disk, right? So we're going to go ahead and label the height of this rectangle as r. Why? Because when I revolve it around the axis of revolution, that becomes the radius of my disk. And then the width of the rectangle, we're going to denote by W. So again, when this rectangle is revolved about its axis of revolution, it forms a three-dimensional disk. So let me go ahead and try to draw this disk. Draw a little bit thicker. Draw this disk as best I can. Oops. This is the axis of revolution. And then here would be like the rectangle that was revolved. All right, and it revolves around this axis of revolution to create this disk. Okay, so we're interested in volumes. So first, how do we find the volume of a disk in general? Well, a disk, really this three-dimensional disk, is a cylinder. So the volume of a cylinder in general is going to be pi r squared times the height. Why? Well, we take the area of the circle, right? And then we multiply it times the height of the cylinder. And that gives us the volume. Right? So that's in general. Now say we want to find the volume of our specific disk. Well, remember that we'll have pi, and what's the radius of our disk? This radius here is r, big R. So we do pi r squared, and then again the width of our rectangle, which is the width of that disk, we label by W. So the volume of our little disk there is given by pi big R squared W. Okay, so again, the idea here is that we have these solids of revolution, and we're going to use the integral to somehow have a nice answer for the volume. So before we jump into that, let's think back to what we did to use the integral to find the area, right? So in general, say we had this graph here. We'll call it f of x, and say we wanted to find the area from A to B. So let's go ahead and fill in that area. Blue this time. So say we wanted to find this area here. Well, remember what we did was first, in order to estimate it, we put a bunch of little rectangles underneath this graph. Right? So we estimated it by saying, okay, we have one rectangle here, and we put, like, say, n rectangles underneath the graph, right? Remember this whole idea of a Riemann sum. So we said the area was equal to the sum, if we put n rectangles, in this case in my picture I drew 4, but and it's the area of all the rectangles, so the adding up the n rectangles, but remember the area of a rectangle is the height of rectangle times the width of each rectangle. So when we did this analysis before, we called the width of each rectangle delta x. And then how did we find the height of each rectangle? Well, the height of each rectangle corresponded to the function value f of x at some initial value. So say this is xi, some x value in there. Well, we found the height of each one of those rectangles by plugging it into the function. Right? So in other words, we got something that looked like this. F of xi times delta x, where this is the height of each rectangle, this is the width of each rectangle. And the more and more rectangles we put underneath the graph, the better our estimate got. And if we went ahead and took the limit, well, when we took the limit of this, that gives us the exact area underneath the graph, if we could put infinitely many of those rectangles. And when we did that, remember this summation symbol kind of became the integral, and this delta x became the dx, and that's how we got the area underneath the graph. Right? So the area underneath the graph is the limit of adding up infinitely many of these rectangles. Well, a similar thing is going to happen here. Now we're going to have some solid of revolution, and we're going to put a bunch of little disks inside of that volume, inside of that solid of revolution, and then if we add up the volume of each of those disks and infinitely many disks, we will get the volume of that solid. Right? So it's a very analogous process here. So say this is our function here. I'm going to call it r of x, and you'll see why in a second, but that's our function. And here is, let's do black. Here's our graph from A to B. And we want to revolve this area from A to B that's underneath the graph around, say, the x-axis. Right, so let's revolve it around the x-axis here. Well, what we can do, again, we'll end up having this solid that's revolved around the x-axis. So I'm going to kind of draw it in dash mark here to try to remind you that this isn't a solid that's been revolved around. Is we can put a bunch of these little disks inside. Right, this is the disk after it's been revolved. We can put a bunch of these little disks inside of the volume or the solid of revolution, and if we find the area of a bunch of these little disks, right, then we add up the area of a bunch of these little disks. That's going to get, let me try that again. Let's add up the volume of a bunch of these little disks, and if we put a bunch of these little disks in there, our volume will be very close to the actual volume of the solid of revolution. All right? So here's a bunch of these little disks here. So to estimate the total volume would be adding up a bunch of the volumes of these disks. Right? Remember, how do we find the volume of the disk? Well, it's the area of the circle times the height, or oops, spelled it wrong. Height or the width of each disk. All right? So again, what is the area of the circle? Well, the area of circle is going to be pi r squared, but how do we find the radius of one of these disks? Well, the radius is going to be the function value, right? The radius of one of these disks is going to be r of x, right? Or r of xi, depending on where we put that xi at, right? Say this was xi, right? So pi r of xi, whatever our radius is squared, times the width of each one of these pieces. Well, just like in the case where I had rectangles, the width of each one of these disks is delta x, right? So adding up n many, say like 5 or 6 of these disks, the volume of these disks would give us a good estimate for the volume of the revolution, right? Adding up infinitely many of these disks gives us the exact value for the volume of revolution. And that's the idea here for our formula. Remember, when we take the limit as n goes to infinity, what happens is this summation sign turns into an integral, and this delta x turns into a dx, and we have our formula. Right? So to find the volume of a solid revolution using the disk method, we use one of the formulas below. And here's the formula. The formula here, if we have a horizontal axis of revolution, just like we did in the picture above, the volume is going to be V for volume is equal to pi, because the pi is a constant. Then the summation sign turns into the integral from a to b, and then we get our radius function squared, and then the delta x changes to a dx. Right? So again, let's draw a picture to show what's going on here. Is we have, say this is our axis of revolution. Say this is our nice function here. This is our r of x. Guess we don't really need that arrow there. And say this is our starting point A. Here's our ending point B. And we're, again, this is a horizontal axis of revolution, so we're revolving it like that. So say we want to find this area that's underneath and revolve it about the x-axis. It's going to take a while. There we go. What we can do is we put these little rectangles in there, right? And these rectangles are going to end up being revolved around the x-axis to create a bunch of little disks, all right? So the height of each one of these rectangles that will be revolved around to make a bunch of disks is r of x, and then the width is delta x. Why is it delta x? Because this is a horizontal axis of revolution, right? And again, we'll find, we'll take this rectangle here and revolve it around to make a disk. A bunch of those little disks give us our volume of the entire solid of revolution. How about if we have a vertical axis of revolution? Well, in that case, our formula stays the same. I'm going to go from C to D here since we're changing up a little bit. But if we have a vertical axis of revolution, our function would be in terms of y, right? And I should square that, right? So let's draw a picture of that so we understand what's going on here. Here's our axis of revolution. Let's draw our function here. Right. Here is our ending point D. Here's our starting point C. And let's draw the area underneath here. Oops. The area underneath here. We're going to take this and we're going to revolve this area around a vertical axis of revolution, right? So when we do that, our rectangles that we get look like this, right? And again, this rectangle is going to be revolved around the axis to give us our disk. Now the width is going to be delta y because it's a change in y. And then again, our height of that rectangle is going to be r of y. Again, because this function is r of y, if it's a function of y. So it's the exact same formula, it's just in terms of y. Okay, great. So now let's practice. So find the volume of the solid formed by revolving the region bounded by the graph of f of x equals the square root of sine x and the x-axis about the x-axis. So first let's draw what we've got going on here. So this is our equation, or I'm sorry, our axis, and then the sine function, remember, goes through the origin and stops here, right? I should probably do this different color. It goes through the origin and stops here at pi. So this is the square root of sine x. The square root, remember, just is going to make those values smaller. So this one's going to be a little bit shorter than the regular sine function. but as far as what the picture looks like, it will look very similar. So let's go ahead and color in the area that we're concerned about here. This is our area, and we're going to revolve this area. I probably should mention here that this is the x-axis. We're going to revolve this area around the x-axis, so this right here. Okay, and we need to make sure that we know those values there, because that's where we're going to start and finish our volume. So how do we find those values there? Well, when does the square root of sine x equal to 0, right? In order to find those points of intersection, we need to determine when this graph here runs into this x-axis there, right? And the x-axis, it has a y value of 0. So we set the y value square root of sine x equal to 0. Square both sides, I'm left with sine x equal to 0. When does sine equals to 0? Well, sine equals to 0 at x equals to 0 and x equals to pi, right? So this value here is pi, and this value here is 0. And now it's just a matter of determining what our radius function is, right? So we need to find this solid of revolution, so we put our little rectangle here in. And now this rectangle will help us determine our radius, because remember, the height of this rectangle is our radius, right? So I'm going to draw a little dotted line here to say that, well, that's a terrible dotted line, isn't it? Try it again. Draw this dotted line to say that that's our radius function. And how do we get the radius of each one of those rectangles, or the height of each one of those rectangles? Well, that comes from radical sine x. Right, so in this case, our r of x is equal to radical sine x. So now it just becomes a matter of plugging into our formula here. Our formula is pi, the integral from a to b of whatever our radius function is, squared dx. Pi, the integral, where do we start? We start at 0, we go to pi, and we take radical sine x, and we square it dx, right? So this becomes the integral from 0 to pi of sine x dx, which I won't waste our time going through it, but it ends up being 2 pi. Okay, and so